the next one is a hierarchical clustering. That's a natural split. Just you can do top down, bottom up, and we have a few here. Let's just run through in case later on you need to use it. There's two ways to represent that. One is use those circles. Another one is dendograms, like this. Or you can use the directory tree, like your how to organize your windows. Well, some field, like in biology, if you wanted to do the taxonomy, like kingdom, class, and family, species, you need the hierarchy. That's one thing. You organize your gene pool, you need some kind of hierarchy. That's why we need it. So, how do you do it? You have two ways. Aggressive, which means bottom up, device is top down. The key word is measuring the similarity, because the split or merge, if they're very similar past the threshold, you merge them. If they were very dissimilar distance, you split them. How do you measure? That's the whole answer. The rest of them is very natural. You can start like at the k-mean, just 2, then 4. You can first, like, let's use k-mean, 2 groups. From one group, then 2 groups. After 2 groups, then each group you group again in 2 groups, 2 groups, 2 groups. Then you're going to have built this diagram for binary tree, right? That's how you can naturally do those hierarchy. Compute the proximate. Proximate means the neighborhood, how close the distance is. So for each data point that be a cluster, that's a kind of bottom up. Everybody is their own center in the beginning. That's 0. And then you repeat by merging 2 clusters. In this scene, when you start to merge, and then you're going to have a new center. If you want to use k-mean, you could actually add your total error. But you can always set off with your gain of the information compression. That's like the galaxy. Why we want this galaxy? We're going to treat the millions of stars as one galaxy. That's condensed all those data into one. And you can think that the whole mass is just located at the centroid, right? That's compressed the information. So you compress the information, then you reduce the cost to encode this information. That's the gain. Again, the minimum description principle. So each time you merge the 2 closest clusters and the 2 by 2, then update the proximate matrix, basically measure the distance or similarity. And then until you find a single, that's one way. And if you're doing the top down, you're going to start this to that. Okay, so very simple thing. Don't have a lot of time, just look at this. 1, 2, 3, look at those dots, how many points? 12 points. And then you start from the distance, you need to look all the 12 by 12 in the beginning. And then how you can merge. And then in the end, you got a 5 to 5, and then the 12 because you got 1, 2, 3, 4, 5 clusters. And basically, these 5 clusters, you can either update this to the center, look at the distance to the center, or you look at the closest distance, minimum distance between them, or maximum distance between them, or average distance between them if you use the centroid. That's all up to you. And then you update this matrix. So distance. If they're very close, you merge them. Then you close this. Oh, the 2 and the 5 are pretty close, and then you're going to make this the next 2 and the 5 now unit as one group, and you recalculate those distance. That's the computational part. And keep doing. So You could choose minimum, maximum, group average, distance between centroid, you count. There's a lot of ways to do it. Depends on your domain to choose what measurement. That's why you say we can produce all the algorithms. That's not true. You, based on your domain, you can change all those formula. Most likely, if you do a real research, you're going to bring the wake codes, and you're going to say this distance function is not what I want. Depends on my field. I need to change those measurement. Then the algorithm does not change. It's a framework. The search, the way to search, the way to organize does not change. But that change will make a significant difference. How are you going to measure your similarity? They're not going to be impossible to cover all different ways to measure it, right? They're all based on your domain. For example, in some domain, I need to give some weight to different group. And you can do that, but you have to write your own code. It's not hard. That's why they have this third part. They have this open source. You can look at the codes and you can combine, you can do it again. That's what the research is. You're not going to just use Weka. You use their library. Make sense? So those things all up to you really depend on your understanding of domain. You can do this way, you can do that way, which one better? It really depends on what you're doing. So those calculations, it's each time, those they already built up, and as long as you define the function, you're good. And then you group them together, subgroup start from 12, 5, then I would count it 2, and the end is 1. So use minimum distance in this, we're going to look at the file in this way. The strength of minimum distance is if the points are this good, the minimum distance will be grouped this together. That will be the strength. You see, the point is you here have no noise point. If you have a noise point, you screw up. Not that. But look at this. You use minimum distance, you won't get anything good, because those are very close with the noise, right? So that's, then you look at the maximum distance. You can do the same job, but you look at the maximum, put it together into comparison. The maximum distance will have no trouble to do this, because they're going to measure to here, right? And this go to here, right? But they're going to have a problem for this. Why? Because that mesh distance is very heavy. Are you with me? They're going to group this together. Can you see it? Right? Because you're going to maximum distance that's shorter than from here to here. They're going to not friendly to this unbalanced big group. Because the bigger group, even inside the group, will have a huge maximum distance, right? Make sense? So another way is this like correlations of the points. Look at this. You can use cosine distance. For example, in the natural language processing, clusterizing the documents, you basically use the cosine distance between the words. Because if the article have the same words appear together, you're going to dot product, you're going to have something. If they never have the same words in the document, you dot product, they get a 0. Get it? In that way, you can measure the similarity. And there's another way. It's called the words method. I don't think we get the time to go to those. If you want to research later on, you read the chapter. That's the 4 different ways. And the group average, mean, maximum, that's easy to understand. Words method basically look at the shortcoming of each, try to balance a little bit, make a trade-off between those things. Somebody, if spend a couple of years with a few PhD students, you bet they're going to find a better way. Research is all about find the shortcoming of some method for something and then improve it. That's probably end up words method. Did you see the difference? The minimum 1, 3, the 1, 5 is here. That's the 6, 3, 2, 5 in each group, they're grouped because they're very close. But however, in this one, 4 is in this cluster, 4 is out in this, and 4 is this. This looks like similar, except the 1 is grouped here in the next. This is out, right? And that's a little bit of difference. So the calculation is not bad. N squared, NQ. NQ depends on how many points. If it's billion points, NQ is huge. But if you kind of for like a business, not bad. Business, you talk about customers, customer groups. You talk about usually millions of customers. You build a Walmart center, let's say. You talk about millions, right, in a city. And then you need to classify those people, and you're going to really, in the end, when you import this product, who you're going to sell to. Especially when the people produce the boat. They really target a very small percentage of people.